mentioned, been giving talks, I think, just about every year since you've been doing star parties. Um, and so the very, very first talk I gave at UBAR was called Black Holes Don't Suck. And it was many years ago. And there have been some advancements in what we know about black holes since then. So I decided to reprise this talk and call it Black Holes Still Don't Suck. And so I'm going to give you some updates as to what we've learned in the intervening years. And of course, the biggest news has been that we have now directly imaged a black hole, and here it is, the black hole of M87. Um, so I hope you can see my cursor here if I'm sharing the screen. So here's the black hole and with the accretion disk around it, and I'll talk more about accretion disks in a bit. But I wanted to explain a little bit about what you're seeing in this image. But first, I also wanted to give you an appreciation as to how big this thing actually is. So here is the image and to scale. So there's the orbit of Pluto, where Voyager 1 is now so this is relative to the solar system. So this thing's a monster. It's one of the largest black holes we know of. And there's a very easy conversion. If you know the mass of the black hole in solar masses, so one solar mass is the mass of the sun, and I'm going to use solar masses a lot during this talk. So one solar mass is the mass of the sun. Um, that means the event horizon would be 3 kilometers in radius. So for every solar mass, you add 3 kilometers to the radius of the event horizon. So if you're not familiar with metric, 3 kilometers is just a little less than 2 miles. Now, M87's black hole is 7 billion solar masses, so 7 billion times the mass of the sun, which corresponds to an event horizon radius, so the radius of the black hole itself, of about 21 billion kilometers. So this thing is a true monster, and one of the biggest black holes we know in the universe. And it's not that far away from us. This galaxy M87 is a pretty close neighbor. So that was the first one we ever imaged, and now we've imaged just recently a second one, our very own black hole. So the Milky Way's own black hole. It has a formal name. It's Sagittarius A star. If you're wondering, the A star denotes a radio source. So this was detected in radio waves, and as many of you might know, the center of the Milky Way is in the constellation Sagittarius. So this is the uh, brightest first radio source that was discovered in Sagittarius, and it happens to be our own black hole. So that's its name. Its mass is considerably less. It's only 4 million as opposed to 7 billion solar masses, which corresponds to an event horizon radius of 12 million kilometers. So considerably smaller. So here's M87, and here's Sagittarius A star. So there's Mercury's orbit, and it would all fit right in the middle there. So significantly smaller black hole at the center of our own galaxy. But now we have two images, direct images of black holes. So what are we seeing here? Well, so I hope all of you have seen the movie Interstellar. And if not, you should, because it's a very good movie. But Interstellar has the rendering of a black hole in it that is the most accurate rendering of a black hole we've ever experienced. It was done by a man by the name of Kip Thorne, Dr. Kip Thorne, who is probably the leading expert of black holes in the world right now. He worked with Stephen Hawking and was a collaborator with him um, back when. And of course, science could never get the money to make this type of computer simulation, have the finances and the resources and the computing power to do it. Science could never get that kind of funding. So Hollywood ponied up for it and had no problem paying for it. And so they paid Kip Thorne and a supercomputer to make this rendering of a black hole because they wanted it to be accurate. And so this is what Kip Thorne came up with, the bottom picture here. Now, why doesn't it look like the movie Interstellar? Well, the Interstellar producer said, well, the actual black hole wasn't very exciting, so they Hollywooded it up a bit and zhuzhed it up as we do out here in California to make it better, quote unquote, better for the movie. Um, so why doesn't this? So what you're seeing here is actually a distortion from gravitational lensing, and I'm going to explain gravitational lensing later on in the talk. So keep that in mind. Um, but what you have is an accretion disk around the black hole. So things don't just fall into a black hole, it's just gravity. But gas, dust, stars, if it's a galactic black hole, can't just fall directly into the black hole. They have to spin around the drain for a while. And as they do that, they heat up, it becomes a very hot plasma, and so you get this disk that's spinning around the black hole. And the disk that's behind the black hole ends up getting distorted from gravitational lensing. Every time you have something massive that's sitting in space, anything behind it will get distorted. If you imagine you were seeing my video, because I turned it off, but if you were looking at my face in the video and I had a black hole sitting in front of my face, you would see my face looking like a funhouse mirror. It would be distorted as the light from me warped around the black front, and then above it is this warped image of the disk from behind, and below it is the warped image of the disk from behind as well. So as that light kind of funhouse mirror bends around the black hole itself. Now, if you imagine that instead of looking at this edge on, you tilt it so you're looking up over the top of the accretion disk, you would have the top warped image above, the bottom warped image below, but then the real accretion disk would then also be below because you're looking down on it now. And so that's what you're getting with this event horizon view. You have the warped disk above, the warped disk below, plus the real disk as you're looking up over the edge. So, what is a black hole? Well, it's a compact, massive remnant of either a massive dead star, which I'll talk more about in this talk, since that was primarily what I studied for my scientific career, or you can have it from a galactic, so like M87, the Milky Way black hole. Those are galactic black holes. And there's really kind of this dichotomy of the two. You have the stellar black holes are a few 10, 20 times the mass of the sun, typically. You'd have a galactic black hole that's a million or a billion times the mass of the sun, but there's not a whole lot in between. And that's still a mystery as to why that's the case. We know of a few that are 10,000 times the mass of the sun, but it's literally a few, just a handful of them. There's not a whole lot. And these kind of intermediate mass black holes are kind of a mystery as to why these don't exist, or really don't exist. One yet to be solved. And I just want to mention that, so as I said, the title of my talk, Black Holes Still Don't Suck, because it's just gravity that's pulling into the black hole. It's the more massive the black hole, the faster you'll fall in, but that's only gravity. Black holes are not a vacuum. They're not sucking things in. It's just gravity that's causing the infall of matter. Just as anything else, if you get too close to the sun, you'd fall into the sun. Rockets that go up in the air, if they're not going fast enough, they'll fall back to Earth. Same principle. Excuse me. So how do you make a stellar mass black hole? I'm not going to go into the galactic ones. I didn't study those. And for the sake of time, it would take forever. So I'm just going to talk about the stellar mass black holes and how do you make one. But first, we need to talk about the sun. So the majority of stars, like our sun, have a balance of forces. Gravity is trying to collapse the star inward, but there's a nuclear reaction going on in the center of the star that is causing nuclear energy to go outward. And so as long as you have the outward energy balancing the inward energy, you have a happy and stable star like our sun. In massive stars, because they are much more massive, and we're talking 8 times the mass of the sun or more, and the or more can be up to 200, even 300 times the mass of the sun, that's a lot of mass, which causes a lot of gravity. So that gravitational force is really trying to collapse that star. So you have to have even more nuclear reactions going on in the star to balance that infall of gravity. So these massive stars are not just doing hydrogen into helium, but helium into carbon and oxygen into neon and magnesium, up to silicon, sulfur, until you get all the way up to iron. Now, iron is the most stable element on the periodic table. The star can't do anything with it. It takes energy to make a higher element on the periodic table. It also takes energy to fission it into something smaller. So the iron just sits there and the star can't do anything with it. So eventually the star runs out of fuel. It makes a critical mass of iron, and there's not producing enough nuclear energy to halt the gravitational force trying to collapse it, and the whole star collapses. All of the star's atmosphere, outer atmosphere, the core collapses in on itself, It rebounds off that iron core, just like if you dropped a bouncy ball on the floor, it would bounce back up very high. Same type of thing. It bounces off that the atmosphere and core of the star bounces off that iron interior rebounds, and the resulting energy blows apart the entire star, and you end up with a supernova. Supernova are truly energetic. They're some of the most energetic explosions. They're most energetic explosions we see in the universe today. So here's an example of a couple. So supernova 2012 AW. Here's the galaxy minding its own business before the explosion went off. And so here's the star going off. You can see how bright it is compared to the rest of the galaxy. Extremely, extremely bright. This one I'm kind of partial to because I wrote a paper on it. So that's my own personal story. But to give you some idea of how much energy that is, it's 10 to the 44 joules, but that corresponds to 2 times 10 to the 41. So that's 2 followed by 41 zeros tons of TNT went into exploding this star. It's equivalent energy. So truly, truly massive explosions going on throughout the universe. And we see these all the time. We had one go off practically next door to us, supernova 1987A. This one was close enough we could see the star before it exploded. It's that one right there, that little dot. And then there's the during the explosion when it was happening. Now, since this happened in 1987, we know it was that star because in the intervening years, the explosion, of course, has died away. There's now a debris field in its place. And we've looked at this spot again, and lo and behold, that dot, that star is gone. It's no longer there. So we know it was that star that caused this explosion. Um, so this is kind of a cycle of life. So you end up with a supernova. The remnant of the supernova within the debris field is usually a neutron star or black hole sometimes. And then you have this kind of recycling of material. So you have these heavier elements on the periodic table get created in this supernova explosion and make a nebula, which then can go make new stars. So this is kind of the cartoon picture we've been shown for a while. And maybe if you've ever taken an astronomy class, you were told way back when that every element on the periodic table heavier than iron was created in a supernova explosion. So gold, silver, lead, all of these elements were created from an exploding star. And I was told that 20 years ago too. Well, that's not the full picture. And turns out the universe is much more complicated than that. And that's not what is true anymore. We have an updated periodic table now. Turns out it's not the case. So even dying low mass stars, so things like the sun can make heavier elements in the process of them dying. They don't explode. Our sun will not explode as a supernova, but it will die one day and make a planetary nebula. We have exploding white dwarfs now. These are called supernova 1A, which I'm not going to talk about in this talk. They just explode. There's nothing left over after they explode, except a debris field. But they also make heavier elements. So here's the supernova, the exploding massive stars. And now we know, because of gravitational waves, which I'll talk about in a minute, we know about merging neutron stars. And we actually think merging neutron stars might be a dominant force in making these heavier elements now, not just supernova explosions. So compact object. So a compact object is kind of a general term for a neutron star, black hole, usually even a white dwarf is called this. And so that's what's left over. If you have a high mass star, it explodes. So after the explosion, you have this debris field. So those of you that are the amateur astronomers, or I say amateur, you observe better than I do, have looked at the Crab Nebula probably. And so here's the debris field of a supernova that went off in the 11th century. And then right in the middle is this neutron star right there with its accretion disk around it. So things are slowly falling onto the accretion disk. And some of the material gets sped up and shot away in these jets. I'm not going to go into the mechanics of jets, but we typically, around neutron stars and black holes, we also see these kind of jet features. So there, that's kind of the typical picture of what's left over after a supernova explosion. So as I mentioned, gravity was trying to collapse the stars like the sun and these massive stars. The sun is going to end its life. It doesn't have nuclear reactions going on anymore. It's actually the rigidity of an electron itself that's holding it up against gravity. So it's electrons that are preventing further gravitational collapse. In a neutron star, it's the neutrons that are doing this instead of electrons. Just too strong, and the whole thing just ends up collapsing in on itself, and you end up with a black hole. Now, I mentioned earlier gravitational lensing. And so anytime you have something massive, it doesn't have to be a black hole per se. The sun does this, the earth does this. Um, it kind of warps space and time. And so this was the heart of Einstein's theory of general relativity was this replaced Newtonian mechanics. You know, Isaac Newton came up with gravity in the 1600s, but Einstein said, no, we have to think about space as like a rubber sheet. And this is actually a really bad analogy, but it's the best one we have, so we keep using it. So imagine the bowling ball and the rubber sheet analogy. It bends space-time, and so light has to travel along this sheet. And if the sun wasn't there, the light would travel in a straight line. But because the sun is warping space and time, uh, it looks like the light is coming from a different position. So the star appears to be in a different place than it actually is. And so when you looked at the black hole earlier, you were seeing that with the accretion disk. The accretion disk isn't above and below the black hole. That light's been bent around the black hole, so it looks like it's above and below, even though it's actually in the same plane as as the rest of the accretion disk, and it was edge on in that view. Um, So this was proven by a solar eclipse in 1915. Sorry, in 1917. So the theory of relativity came out in 1915. This was proven in 1917 from a solar eclipse of 1919. And conveniently, the solar eclipse happened right in front of a very well-known star cluster called the Hyades. It was an open star cluster, hundreds of stars, and we knew the positions of these stars very well. So when the moon blocked out the sun, you could see the stars behind the sun now that the sun was dark. And lo and behold, those stars were in a different place that they were supposed to be by exactly the same amount that would correspond to the known mass of the sun, to within errors. So as soon as the sun moved out of the way, the stars then moved back to their correct positions. So this was, the first proof that Einstein was in fact correct. So every time you hear on the news, oh, Einstein was proven right again, it's like we proved this in 1919. Einstein was right. General relativity is correct. So here's a photograph that was taken by Arthur Eddington of the solar eclipse. And then you can kind of see these little hashes. They're very faint next to it. And those are the actual stars that are being measured. Their positions are being measured. And of course, we had a solar eclipse in 2017. I went out to see it. And here's my photo of the solar eclipse. Unfortunately, I couldn't see stars. I was not on the center line. I was off a bit, so I could not see the stars in Tennessee. However, lucky you, there is an eclipse coming in 2024. You may have heard of it, and it's going right over U bar U. So U bar U will be very close to the center line. You should be able to see stars around the sun, so that's going to be exciting. You can recreate and prove to yourself the theory of general relativity. So here's the information for U bar U. This all came from an app called Totality. I get no kickbacks from any of these apps. I just use them and find them useful myself. So here's the line. It gives you a Google map of where the center line is. And I've marked where U bar U is. And here's the center line of where maximum eclipse is going to happen and the times there. So if you want to see all this, I recommend this app, Totality. So So that was the example I gave for the sun. But if you have something that's more compact and more massive, that dip is going to become more and more pronounced until eventually it becomes infinity when you have a black hole. This is where the kind of rubber sheet analogy breaks down, because if you can't have just an infinite hole going through a rubber sheet, um, that's kind of nonsensical. But that's what happens in the analogy. Um, so the event horizon is where light, the escape velocity of the black hole is equal to the speed of light. So we tend to use the event horizon as the quote unquote radius of the black hole. So it's where, just as the Apollo astronauts had to go faster than Earth's escape velocity to get to the moon, to escape from Earth's gravity, um, in their large Saturn V rocket. While taking off from the moon just required that smaller lander, because moon has less mass, less gravity, so you didn't need a big Saturn V rocket to get off the moon. You needed a big Saturn V rocket to get off the Earth. If you were at the event horizon of the black hole, you would have to have a velocity equal to the speed of light to escape the gravitational pull of the black hole. So that's the definition of the kind of the radius of a black hole. So I want to very briefly, I'm going to talk about gravitational waves. And to do that, I need to introduce the concept of binary stars. So a binary is just anything that orbits around each other. They orbit around a common center of mass. So um, in the case of two equally mass objects, they orbit around this common center. If they're not equal in mass, like a star and a planet, for example, you will get this wobble effect. And by the way, the sun and Jupiter do this. So this would be like this: the sun does not stay stationary; it actually has a wobble. And we can measure that wobble due to the pull of Jupiter, and we can measure the wobble due to the pull of Saturn as well. It's smaller, of course, but it's there. Um, And so when you have one of these objects is a kind of compact object called a black hole or neutron star, um, we could if these objects get too close to each other, the black hole or neutron star can actually suck off, not sucking, of course, it's gravity, but suck off the atmosphere from the neighboring star, and it spirals down the drain, makes a accretion disk before falling into the black hole or onto the neutron star. This accretion process ends up heating this gas to very hot temperatures. It radiates very brightly in the X-ray, and so it's called an X-ray binary for that reason. The primary light coming from these systems is in the X-ray, and of course, there's two things, so X-ray binary. These are kind of near and dear to my heart because I did my PhD dissertation on these. Um, So you can have two compact objects as well. So it's a case of a white dwarf and neutron star. These tend to be very small objects. So kind of there's the Earth for size comparison and the sun. So they're quite tiny. You can have a neutron star or even a black hole. And when you have a neutron star or black hole or even neutron star black hole and a black hole, one of each, as we have now seen as well, you can make gravitational waves. And so, what's a gravitational wave and how do we detect these? Well, the first gravitational wave detector was called LIGO. There's actually two of them, one in Washington State and one in Louisiana. These arms are 2.5 miles long. And so, what happens, and then we have another one called Virgo that was recently built in Italy. And there's one called Indigo that's going online in India in 2024. So, we're going to have four of these shortly around the Earth. And so what happens is that if I go back to this kind of picture here of the neutron star, you can see how they're spiraling around each other. They're causing a ripple in that rubber sheet. So if I go back to that rubber sheet analogy and you imagine a marble or something heavy going around in circles on that rubber sheet, it's making a dip in that rubber sheet, but it's causing a wave to go out from that along the edge of that rubber sheet. And so it's this kind of ripple effect that's going out through the universe, and that's a gravitational wave. So as these two orbit around each other, you have these waves propagating out through the universe. And that actually causes the binary system to lose energy. So these neutron stars or these black holes will actually spiral into each other and eventually merge. And when that merge happens, it's like dropping a rock in a lake. You have this massive event of splash and waves going out very rapidly with a lot of energy. And so that's what we're detecting with these systems. And so how they work is there's a laser beam shown down each of the arms. So it's the same, it's split. So you have one going one way, one going the other way. They bounce back and forth these mirrors, and then they both of these beams end up going to the same light detector. So if the two laser beams arrive at the light detector at the same time, then no gravitational wave has gone through. But if they don't arrive at the same time, then the very fabric of space itself has warped underneath the detector. It's warped the Earth, it's warped you, it's warped me. Uh, and this causes that distortion. So here's kind of an animation showing that. So as the gravitational wave is distorting space, you can think of it's distorting existence itself. The the arms will shrink and expand, and you'll get this kind of flashing effect, whether it's detected or not. Now, this is very sensitive and very slight. Um, the amount of movement is actually smaller than a proton in an atom. So if you think of not even just an atom, but a proton in the nucleus of an atom, it's smaller than that. So it's, I'm sure you've all felt it when a gravitational wave's gone by, right? Um, but nevertheless, that's why these detectors are so large and extremely sensitive, and why we had two of them initially, because if both instruments detected at the same time, then you could say, ah, that was probably something important versus a truck going by, or in the case of Louisiana, they've had gator problems. Um, so it's a checks and balances against it. And now we're going to have four of them so we can triangulate where the wave is coming from even better. So here's the very first gravitational wave, was discovered in 2016. Um, and they've converted the signal into a sound so you can hear it. Now, this was two black holes merging, two 30 solar mass black holes or so. Um, and mind you, this was probably the most energetic event we had ever observed in the universe up till this point. Okay, so keep that in mind. You have two black holes merging and merging and merging, getting close, spiraling in, getting closer and closer and closer and closer and closer together until at the very end they become one giant black hole. Um, so that what you're hearing is the increased frequency and speed of the ripples in the rubber sheet as those black holes merge closer and closer together. So I'm going to play it. It gets a higher pitch at the end of the frequency. It's a little faint, so hopefully you can hear it. So this is from the two different detectors. So here's the increased pitch. So it's the chirp. And the amazing thing is that the frequency that black holes happen, this frequency is actually in a range of human hearing. So it's not modulated at all. This is actually the sound of a black hole merging, which I always thought was kind of interesting. So that was the most energetic thing in the universe we had ever detected up to that point. I know it's adorable, but there it is. And now we've seen, of course, dozens, if not hundreds, of these mergers that have happened since. And we have also seen now a neutron-neutron star that's been confirmed. And this is exciting because we thought gamma ray bursts. So I hadn't talked about gamma ray bursts, but we have gamma ray telescopes up in space, and they were detecting flashes of gamma rays coming from the universe. And it was theorized for a long time that these flash of light of these gamma rays were coming from a merger of two neutron stars. And lo and behold, we now coincidentally saw that happen. So Fermi and Integral are two of these gamma ray burst detectors. So it saw a burst, a gamma ray burst happen in this galaxy here, and there it is happening over the course of a couple of days. Um, their observations of it, and then LIGO Virgo said, "Oh, yep, here's the chirp. We've seen it, and it happened at the same time in the same location as that gamma ray burst." So this proved definitively that yes, these gamma ray bursts are one flavor of these gamma ray bursts are in fact neutron star mergers. This also proved that gravity and light move at the same speed, which we kind of always figured was the case. Um, so you may have heard at one point that if something catastrophic happened to the sun is 8 light minutes away. So we wouldn't know that anything had happened to the sun for 8 minutes, which is true. It would still look like the sun was shining bright in the sky, even though it may not have been there anymore. Well, it was a philosophical debate for a long time whether if you took some bizarre force of whatever, um, Thanos, whatever, took away the sun, um, and it was gone, we wouldn't know it for 8 minutes by light, but would Earth's orbit be affected immediately, or would it take 8 minutes? Turns out it would take 8 minutes. Gravity and light move at the same speed. Um, so that was a philosophical debate for a long time, and it was conjectured that it was probably the same, and turns out it is in fact the same. So LIGO detected the gravity, Fermi and Integral detected the light, and sure enough, they arrived coincidentally. So I want to finish up a little bit with some breaking news that we've had recently in black holes, since I was going to update all of this. So we've seen a rogue black hole now for the first time screaming across the Milky Way. Sometimes, you remember I said that supernova cause neutron star or black holes as remnants. Well, we have seen rogue neutron stars for some time. Sometimes the supernova explosion doesn't happen cleanly or symmetrically, and there's a preferential energy explosion direction. So it will shoot out the neutron star like a cannon. And we've seen rogue neutron stars flying across the galaxy at tens of thousands of miles per hour. But we've never seen a black hole one because they're black. These rogue black holes don't have accretion disks around them. They're black, so you can't see them. But if they pass in front of another star, it will distort, it will make a funhouse mirror of that star behind it. And it can brighten it, it can distort it in different ways. And so that's how we found this rogue black hole. So if you see this animation here, so what's happening when it's bright is this black hole is passing in front of the star, between us and this star, and it's making a funhouse mirror effect of this star. And so we were able to calculate the mass of the black hole based on the distortion of the star behind it. And turns out the black hole is also moving at about 100,000 miles per hour. So you have this dark thing, can't see it, screaming across the Milky Way. And if there's one of these, there's probably a lot of them. So, not a lot. I imagine it doesn't happen that often, but it definitely happens, and we've seen one now. And other breaking news. So now we've had the sounds of a black hole have been heard. This was first done in 2003. Turns out, though, this is a galactic black hole. This is a Perseus galaxy. And there's a large black hole at the middle of this galaxy, and it's causing acoustic waves. It's actually producing acoustic waves, not just light waves, that are propagating through this gas cloud that are around the black hole. So they're very low frequency, beyond the range of human hearing. In fact, the natural sound is the lowest sound that's ever been recorded in the universe. It's actually a B flat, 57 octaves below middle C. So music aficionados, there you go. It's the lowest the lowest sound ever recorded thus far in the universe. But what's happened recently is they've modulated this sound into something we can hear with our own ears. And so I wanted to play that for you. So here's that black hole, and hopefully you can hear the sound of the black hole. So if you're looking for a Halloween soundtrack, there you are. You can put that on a loop. Um, so um, so just to finish up, so we now have two direct images of black holes. We're detecting gravitational waves in copious amounts. There's actually an app for that as well. There's this app called Gravitational Wave Events. It will give you an alert every time a gravitational wave is discovered by LIGO or Virgo. There have been so many lately, I actually had to disable my app because I was just getting too many notifications and it was getting annoying. But if you would like to get those notifications, there is an app for that. So I would encourage, that's a good one to explore. And I'll just finish with this movie. I always like this movie. It doesn't have sound, but so this is a stellar mass black hole, but a very energetic one. So it's on its side. So the accretion disk is running up and down here vertically. As you remember, the Crab Nebula has this jet going from the neutron star. This black hole has a very large jet coming from it. And so you can see that not everything. I like this video because it shows that it's like sometimes people get this idea of things in the universe are static and never changing, and we can't actually see movement. Well, that's not the case. So here's a black hole with a jet. The jet's actually clumpy. You can see bright clumps coming from it. And you can see it rotating. So if you imagine a top, if you started a top spinning, as it started to slow down, it wouldn't be straight up and down anymore. It would go off at an angle, and the axis of the top would start to precess around. So it wouldn't stay vertical anymore. It would kind of spin around at an angle. So that's what's happening with this jet. You're seeing this corkscrew effect. As the black hole spins. So that's my talk, and I'm happy to take any questions.